This is Lecture 9C for Calculus 2 on the use of an integrating factor. Integrating factor is really a trick. It's a trick to make a non-separable equation into something similar to a separable one. To use and find an integrating factor, the differential equation has to be written in the standard form. Okay, dy by dx or dy by dt. So here's the first derivative. This is on the left-hand side, plus some function I'm going to call p of x times y equals some function q of x. Now you see this almost looks separable, except that p is a function of x over here, but it's going to work out. Now, either or both of the functions p and q can be a constant, and you certainly hope they are, because that simplifies your life. Right. The integrating factor is a function nu of x, which is equal to e, and then the power of e, Euler's number, is the integral of p of x dx. Both sides are multiplied by this integrating factor. So I multiply the left-hand side, I would get e to the integral of p of x d of x times the first derivative, plus, I'm here, p of x times e to the integral p of x dx times y, and that equals e to the integral p of x dx times q of x. So I've multiplied both sides of the equation by this integrating factor. This is the integrating factor. Right. Now, here's the trick. Note that we're looking now at we're going to look now at the left-hand side and simplify it. If I took the derivative with respect to x of e to the integral p of x dx, I would get p of x e to the integral of px dx. Ooh, I'm going to get this term right here, and I'm going to use that to simplify the left-hand side. Now I'm going to simplify the left-hand side by recognizing that it really is an example of the product rule of differentiation. So let's note on the left-hand side that we have, this is just the left-hand side of the equation. Get the highlighter here. Okay, this is all the terms from the left-hand side. They haven't been simplified yet. But this becomes, the first term is nu, so I'll write that here. It multiplies dy by dx. In the second case, p of x times e to the integral dp by dx is the derivative of the integrating factor multiplied by y. So this is the product rule. It is the derivative with respect to x of nu times y. So I'm going to rewrite the left-hand side using this idea. So e to the integral of p of x dx times the first derivative plus px e to the integral of px dx times y is equal to the derivative of the integrating factor, here's the integrating factor, and the function y of x. Now we're going to replace the left-hand side with this product. Alright, so derivative with respect to x of e to the integral p of x dx times y of x. This is my left-hand side as I simplified it. It equals that integrating factor times q of x. Wow, and this is what I talked about, that this integrating factor makes things separable. Now we can integrate both sides, and here's what we get. On this side, we're integrating this derivative, so we have e to the integral of p of x dx times y. This just comes forward with integration. On the other side, I have to carry out the integration, which I'm not going to do right now. Instead, I will solve for y of x by multiplying both sides by e to the minus integral px dx. And this is the result that I get. Okay. Notice the change in sign between the integrating factor here. Okay, so here's the integrating factor. But because I've multiplied to move to isolate y of x, I now have the integrating factor, but it has a negative sign in front of that integral. Don't miss those signs. Now the way it looks is very complicated. However, you generally carry out that integration before you even start, and so things don't really look this bad. Here's an example using an integrating factor. For this example, I'm going to use the equation for the current in a series. So here's a resistance, here's an inductance, and right here I have some voltage V. Okay, and what I'm looking for is the current that's flowing here in the circuit. All right, I've got to find that current. And the current's going to change with time. To solve this equation, and just for purposes of demonstration, I'm going to let the resistance, the inductance, and the voltage R, L, and V be constant. All right, but the current's going to change with time. Now, this is a first order linear ordinary differential equation, and I can write it in the standard form. dy by dx plus R over L times I, you can see obviously how to do that, equals the voltage divided by the inductance. And for an integrating factor, we want to have the derivative. I'll say dy by dt plus some function p of y. In this case, it's a constant, so we're fine with that. And here's I equals some other function, which is really a function only of the independent variable. So in that case, R over L is P of Y. Again, I said you like those to be constant. And here is my Q of T is actually a constant, V over L. So here in this slide shows what I said on the other slide, but typed in. So P is R over L, Q is V over L. Both are constants in this equation. We like that. The integrating factor is e raised to the integral of px dx, or pt dt. Okay, this becomes the integral of R over L times dt. But R over L is a constant, so we can go ahead and just carry out the integration and find that e is raised to the R over L times t. And that's my integrating factor. I multiply both sides of the equation by that factor. So here it's times the first term, times the second term, and times the third term. I know there are a lot of steps here, but after you do it a couple times, it's really not that hard. Okay, so the left hand gets written as the derivative of a product. That's what happens to the left-hand side. And my right-hand side I just leave alone as it is. Okay, now I'm going to integrate both sides. And on the left-hand side, by the fundamental theorem of calculus, I get e raised to the R over LT times the current. On the right-hand side, I still get this integral, and I'm going to leave it like that for now. All right. In fact, I can carry out this integration pretty fast, but I'll do that in a minute. So here is your left-hand side, and now I'm carrying out this integration. I get V over L, which is a constant from here. Let me change color. So here's my V over L. That's right here. Then I'm integrating e to the R over LT, and I get L over R, of course, times e to the raised to the R over LT power, plus some constant of integration, which I'm calling A, so as not to confuse it with capacitance later on in electrical engineering. Okay, so I can simplify this a little bit. I get V over R, e to the raised to the R over LT, plus a constant A, which is a constant of integration. Now we're going to solve for the current, and this gives us a general equation. So the current as a function of time is e to the minus R over LT times V over R e to the R over LT plus some constant A times e to the minus R over LT. So I just multiply both sides by e to the minus R over LT in order to isolate the current. I can simplify this a little bit because this is negative, this is positive. Since they're multiplied, I can add those two powers together, minus R over LT and plus R over LT, and get 0. E to the 0 is 1. So this is the equation I get for the general solution. The current as a function of time is V over R plus some constant A, e to the minus R over LT. If I know the initial current, that is the current at time 0, I can substitute that t equals 0 into this equation and solve for A. A is initial current minus V over R. You should recognize the various parts of this equation. Here's that particular solution. The current as a function of time equals V over R plus I0, the initial current, minus the equilibrium value, which is V over R, times a decaying exponential e to the minus R over LT. So we have exactly the same kind of solution that we had for the concentration in the blood. We had an equilibrium value here, the concentration in blood, which is R over K. Here we have an equilibrium or a steady state, you can call it either term, V over R for the current. Then we have these transient terms. The transient terms involves the initial condition minus the equilibrium. Have the same thing here. And then we have a decaying exponential. Okay? So for the current in the series RL circuit, we have an equilibrium value of current V over R. If the initial condition is greater than V over R, you start greater than the initial, then the circuit will decay towards V over R, and the approach will be exponential. If you start with an initial current I0 less than the equilibrium current of V over R, then the current in the circuit will creep up towards the exponential value. And the graph for this looks just like the one for the concentration, but then you would replace 400 on that graph with V over R, which is the equilibrium value for the circuit. This slide is really a style point, but these style points are really important in keeping, they're just very important. What Stewart does is solve problems like this series RL circuit with specific values for voltage and for resistance and for inductance. So when he's done, he does get a solution, but I think it is much better to let the variables R, L, and V stay variables. Don't give them any particular value. The extra variables will not really bother you during the problem. They will hang out there. In fact, they're very handy because you can trace back if you think you've got any error. If you have numbers, you tend to multiply them together, divide them out, and you forget which numbers went where. So it's much better to leave all variables as letters. Don't give them specific values. Solve the problem using R, L, and V. Those letters R, L, and V. Okay? Once you've got the solution, you now have a template. You have a solution for any series circuit, RL circuit, with constant resistance, inductance, and voltage. Then if you have a case where the voltage is 10 and the resistance is 50 and you've got an inductance of a couple microhenries, you can just plug those values in and you get a solution. You can take your general solution and you can program it into your computer or to your calculator, and then you can solve your specific circuits with that. So that's what I try to do throughout this whole lecture. This is what I try to do in practice, is solve using general variables, using the letters as the variables, create your template, and then you can solve for any particular situations that come up, any particular numbers. Otherwise, you have to go back and redo the whole problem, and who wants to do that?